All right, I'm gonna get started. I'm not sure if anyone is here or can hear me, but I'll keep an eye on the chat and we'll see. So, short recap for those who haven't joined before or are watching the video on YouTube that comes after the stream. Well, welcome. We are doing a lot of stuff lately, building like low-level drivers and low-level communication with different kinds of hardware devices. And what makes that possible is this device called the Bus Pirate. The Bus Pirate, you can think of it being a piece of hardware that, is like, it's like adding USB ports to your computer or something like that. Basically, it opens up a bunch of new ports. And some of those ports are SPI and I2C and one wire and raw wire and all these different things. JTAG in some capacity. And these are basically ports that allow you to talk to specific kinds of devices. But in order to talk to those devices, we have to build the drivers for them because they have to be communicated with in special ways. And we're doing all of this in TypeScript. And yeah, a big part of the reason is because this is low-level JavaScript, of course. But yeah, another part of the reason is that with this tool, the Bus Pirate, and with the kind of the stack that I'm building up of code for the Bus Pirate that allows us to easily interact with these kind of devices, it's basically creating this nice prototyping environment where you can actually like take a device and kind of figure out the communication with that device before you go and implement it in like a microcontroller or something for an embedded system. And that's actually exactly what we're going to be doing today, because I have a kind of project that I have going on, and it's kind of a side project. It's not on the channel or anything at the moment, where I'm trying to build a Game Boy emulator on an STM32 based board. Outputting to like an LCD screen and pulling stuff from an SD card for like the ROMs and the boot ROM and that kind of stuff. And hey KD9KCK, I'm glad you can watch this. Welcome. Yes, so that's kind of like a project I'm working on, and one of the things I want to do is write all of the drivers there from scratch. Right, there are already existing libraries to interact with things like an SD card and things like an LCD screen, and those things exist, but I want to build them all from the ground up. And the Bus Pirate plus this driver stack I'm building in TypeScript makes this really like a really nice iterative, explorative procedure. So that's kind of the idea here. And yeah, so what I've got is and I can show it on camera, but I've got a nicer picture below here. What I've got is kind of like this little SD card module. It's a, hopefully the camera will decide to focus in at some moment. Probably it won't. But no, never mind, because I've got a better photo of this. This is a little SD card module, and it's used typically for like interacting with a device like an Arduino or something like that. And yeah, so it looks kind of something like this. You got your micro SD port here, you plug it in, and you get some pins, and you plug these pins in, and these pins go to an SPI bus. So we've been building SPI drivers in the last couple of videos, but I'm going to go into more detail today about how SPI actually works and like what is going on with the electrical signals and stuff, because it's relatively important to know for this. But yeah, this is basically the module, and what you might notice about this, and I can show you the backside of it on the camera now quickly. Oh, I realize I'm not showing you what this module is. Sorry. This is the module. So what you'll notice here is we've got the SD card entrance, we've got like the pins. There are a couple of resistors there. Those are 10K resistors. They kind of look like they're in line. It's kind of hard to see the traces in the circuit there, but don't worry too much about it. This is what's on the back. It's basically blank, right? You can see there's some silk screen that says the pin names, and you can't read them because my camera just absolutely refuses to comply. But those are the names of SPI signals. So it takes in some power, it takes in a ground signal, and then it takes in MOSI, MISO, CS, and what's the other one? Clock. That's the one. Yeah, so that's it. And there are no chips or anything on this board. So that is like that is a really good hint that like we can actually, there's nothing special going on here. Do you know what I mean? There's no special hardware on this thing. We're basically wiring directly to the pins of the SD card. And let me just show you, an SD card, it's got a load of contacts on the back. Well, as it turns out, those contacts, well, it's a little bit more complicated than this, but SD cards, they have a mode that you can put them in. And this is basically all SD cards, although I think some of the really advanced ones that are coming out now, you get like extremely high volume SD cards. Those ones maybe not. But most of the early editions, and even the ones that have, quite a few gigabytes of memory on them, have a really basic mode that they can go in where you can speak SPI to the SD card, SPI. And that's what we're going to do today. We're going to put the SD card in that special mode, and we're going to talk to it and send it the commands it needs to receive. And it's going to allow us to interact with the low-level storage on the drive. And once we've built that, and I'm not sure how we're going to do on time here, so we'll see how far down the stack we end up getting. If not, we're going to pick this up on the next episode. But when we've actually gotten that stuff done with the SD card, we can build a layer on top of that where we can talk to the file system. Because the SD card just provides storage, right? It just allows you to throw bytes on top of it. And then a file system is basically a special arrangement of bytes, and some of those bytes point to other bytes, and they form a special structure. And that's all the file system really is. And then that's the second part of what we'll get to. And then once we've got that built out, basically we should be able to read and write files to the SD card directly from TypeScript, driving directly the electrical signals via the bus pirate. And yeah, that'll be it. And basically, for me, I'm going to be able to take most of the code that I write here in TypeScript and basically copy it with a few adjustments and have it running in like a C or a C++ project that I would use for the STM32, because most of what you actually do is just define what all of the special bytes that you have to send and exchange are, right? They have special meaning. You just give those names, and then you actually just send and receive bytes. And that's pretty much all you end up doing when you're writing drivers. I mean, yeah, it gets more important and, trickier concepts than that, but that's pretty much it. You're exchanging bytes. So, yeah. Hey, Coder Bob. How do you know so much? Well, yeah, maybe the secret to that is that I personally don't think that I do know that much. And especially on this subject, on the SD card communication thing, it's only in the last couple of days that I've really dived into this. So I have some fresh knowledge that's in the top of my mind. But aside from that, there are probably going to be things that I run into today that I don't know. There's an infinite amount of things I don't know. So don't worry about that. There's an endless list of things that you can't know in this world. But you can know about this. The information's actually there. If you just start Googling SD card SPI, you'll find tons of stuff. And we're going to look at some of that very, very shortly. In fact, actually, let's just begin. Before we begin, I just want to show my setup here with the bus pirate, because I have been working on this in the last couple of days. I have this kind of crazy setup on a breadboard. It's not that crazy, but... so here's the bus pirate, and you see it's got some wires coming off it. Those wires go off onto this breadboard and connect up here, and they're hooked up basically to a part where I can plug in that SD card module, and I can plug in the logic analyzer, which if you tuned in the last episode you would have seen. And I also have an Arduino hooked over here, with a level shifter, because Arduino works on 5 volts and SD cards work on 3.3. So I've got a level shifter there, and I've got basically the same kind of setup where I can actually plug in the module and the logic analyzer. So I've got like a bunch of wire harnesses ready so I can plug the logic analyzer in. And that is basically because I needed a sane place to, like, I needed to see how actual, like how you properly talk to this card. I've been reading a lot of theory, but I wanted to see how the signals were looking. So I've been doing that, like observing the signals on the Arduino and also then applying them to the bus pirate. I'm trying to fool my PS Vita to use my SD card as its memory. Yeah, well, that is something that I don't know a whole lot about. I didn't actually ever have a PS Vita. I do have a Switch that I've hacked, and that does run like everything from its SD card. But I don't know too much about the Vita. Are you doing it? Have you like hacked the Vita? Do you have like a homebrew setup on it, and you're trying to like load things in from that? I'm interested in that. All right, so that's my crazy setup here. Let's go back to the browser, and I just want to show you kind of where I ended up. So my first step here, the first step was that when I looked at this board here, I noticed there was no chips on it. So I knew that it had to basically, the SD card had to be doing SPI, because you know, this thing is an SPI module. That's what I bought it for. And I'm looking at the signal names on the thing, and I see, okay, they're the SPI signals. But there's no chip, so there's no like translation layer going on here. It's not like you know, I'm talking to a chip that then talks to the SD card in its own language, and I'm talking to that chip in SPI. That's not happening. So I knew that the SD card must actually speak SPI natively. So I started Googling it, and one of the results that I found was this amazing page that has so much good info on it. And I'll try to remember to link these things in the chat. So if you're watching this in the future, not in the chat, in the YouTube comments, if you're watching this in the future and I haven't left these links, please just nudge me and say, like, put those links in the description and I'll actually do it. So here, yeah, this is basically a page that gives you a ton of information. And so, for example, it shows you that, like, hey, here's an SD card and here's an MMC card. That's something very, very similar to an SD card. That here's an SD card and here's what those pins mean. And you can see here they've got special names on the side. And there are actually, although the SD card can speak SPI, it natively has its own special like SD card protocol, right? Because SD cards inside, they have a microcontroller. They actually have a tiny little microcontroller. And there is an amazing talk online by Bunny Huang about basically he bought hundreds of different kinds of SD cards and cracked them open, found all these different microcontrollers inside them, because it controls like how, you know, where it's going to store the bytes and how it like does wear leveling, which is a concept in SD or in Flash itself, like flash memory. You can't write the same bytes over and over again, otherwise you'll wear out the memory. So it has to do like put the bytes in different places. So that's what that microcontroller does. And he actually went and like found this microcontroller, reverse engineered it, and basically made a framework where you can program the microcontrollers of an SD card. It's kind of amazing. I'll try and remember to link that as well, but you can Google that. Bunny Huang, super cool stuff. But yes, so there are, as you will see here, SPI signal names, and they're linked directly. And one of the cool things you can do, right, is you can take one of these SD card adapter. I feel like I have hundreds of these lying around that I've accumulated over the years as I've bought like micro SD cards to go in phones and different devices. They always come with this adapter, and what you can actually do is just solder some pin headers to these points on the SD adapter, like literal pin headers that you would use on an Arduino. The spacing is actually correct. Solder those, And then you can use that as your SD card adapter, and like you don't need to buy some special module from Adafruit or whatever. You'll just have this ability to do it. So super cool. So that's something we need to know. And yeah, this is going to talk about how we go into SPI mode, like what the commands are going to look like, how we speak to the device, how we have to wire it up. There is a consideration to be made in that when we wire up, this is microcontroller here, but this is going to be our bus pirate basically. So you will wire up the chip select, the clock, the data in and the data out. And you need to have what's called a pull-up resistor on the data out line from the subordinate device. And if you don't know what that means, like pull-up resistor, well, go and watch like all of Ben Eater's videos because you'll learn about that and they're super cool. But the short summary and like my programmer summary of this is that a pull-up resistor or a pull-down resistor is basically when you take... It's like giving a default value to the line that you're on, like the signal line. So if like one of these sides is not electrically connected to the other one, so like say the card is like, there's like a switch inside and it's not connected. Well, it's kind of like it will give this default value. Like it will use this pull-up resistor, which is going off to 3 volts or whatever. And it like this will have a high value on the line. And if you did a pull-down resistor, you're going to ground. You put a resistor going to ground, you kind of pull the line down to the ground in the absence of a real signal. And because of the choice of resistor that you use, this is just an electrical thing. That basically, this you can think of the signal line will favor an actual signal going across rather than the pull down to ground or the pull up to 3 volts. If you're driving a low signal, like a ground signal across, like a 0 volt signal, it will take that even if you've pulled up. That's my tiny summary. So basically, the card requires us to have a pull up there, and that will be present if you have if you plug an SD card into your phone, your phone will have that circuit built in. And if you plug it into an Arduino, you just need to do this kind of thing. So I found this page and I was like, okay, this page, it's everything I'm going to need. This explains kind of like how command frames look like. So when we send commands to the device, there's something called a command frame. So it's not just 1 byte that says, okay, do this thing. It's like 1 byte plus an argument plus maybe a CRC, which is kind of like a checksum that you have to add. Luckily, we don't have to do any checksum calculation here because of some tricks that you'll see. But yeah, we send that stuff, and then there is a period of time, this NCR, where like just nothing will happen, like the device won't respond yet. And then eventually the device will start responding and it will give us some information, and we'll know the kind of format of that information. Yeah, this is the kind of relevant command set. It's not all of the commands, but this is kind of a bunch of the commands that we might use. I think we're only going to use a couple in this video. But this is stuff like software reset, initiation process. There's a couple of different things like sending particular kinds of commands. Read the CSD register, write the CSD register, stop reading data, change the read-write block size, like a bunch of like just low-level control commands that basically say like, okay, this is how we're going to do data read, this is how we're going to write data. And yeah. And then when we get responses, they come in a certain form. So we're basically an R1 response, which is what you almost always get. An R1 response will basically, like, you'll get back a byte, and each position will have a meaning, and it will just tell you what the meaning is. So if we send there's quite some, I think it was a Chinese author that made this page, so some of the grammar and the spelling is not completely correct, but I mean, you can get most of it right. If there's an illegal command, there'll be a high bit here, and we'll be able to check like, oh, was there an illegal command? And sometimes, for instance, we'll get another type of response, which is like type 3 response, where we get this R1 thing, and then we get the OCR register, and the OCR tells us some information about the device. Anyway, let's go to the code. Let's switch it up. Let's go to the code. Let's set this file up and kind of begin the process of writing the driver. So we go to the code. This was my tweet that I put out about the live stream, and here we are in the driver. And I've kind of, in the last couple of days, I've written like bits and pieces of code, so I've got an idea of where this is going to go. I also have that code open in another window, or I can have it open, so if I kind of get completely stuck, I'm not I can hopefully go there and look and make sure I know what I did wrong. But yeah, so what we're going to do is we're going to import some stuff from the library, the Bus Pirate library. So let's do that. Let's well, what I'm going to want is a SPI mode. Yeah, it's not coming in, so that's fine. Import from. We want to go back into the source directory. That's where the Bus Pirate stuff is, and we're going to want SPI mode. And we're going to make here a class called SD-Card. I think that's an appropriate class name. SD-Card is going to keep track of a SPI object, which is going to be like what we use to do our SPI communication. So we'll make that a SPI mode. And I'm going to do something different to what I did in the last couple of videos. I'm actually going to use dependency injection this time around, because if you were going to actually kind of, this is really just to illustrate a concept, just in like kind of a contrived way, but a real world concept that you should do in your production code, and that's you should use dependency injection. So rather than creating the SPI mode Bus Pirate interface here, we'll allow the user to pass it in. And later on what we'll do is we'll actually make this an interface rather than an actual concrete type, and then that way if we wanted to do tests, we wanted to write tests against this system without having to have the real hardware, we can write mock SPI mode classes. Just something nice to do. So we're going to take in SPI, which is a SPI mode. It really wants to bring in those parameters. And we'll just assign SPI to SPI. Just like in the last things, we're going to need an asynchronous init method. We're going to need an asynchronous init method because like we need to do asynchronous stuff to get the Bus Pirate up and running. So it's better to separate it from the constructor, which we can't make asynchronous. So we are going to await this.spy.init. So allow the SPI initiation to set itself up, and then we're going to start doing some code. So a message here, a file system layer means ? A driver which reads from disk. Yes, so yes, that's basically it, right? We're going to have an SD card driver, which is going to build on top of the SPI driver that that's already written for the Bus Pirate. So that's going to make use of that to talk directly SPI to the hardware. And then the SD card driver is actually going to be driving the correct signals to talk to an SD device. So SPI is just a physical format. It's just a physical layer. Like here are some wires. Here's how you send data over those wires. But it doesn't tell you like, here's a particular way, here's a shape of data you need to send over the wire. So every SPI device defines its own protocol, basically. So we are going to speak the special protocol to talk to an SD card. So that's going to be the SD card driver. And then the file system, well, that is like you build on top of the SD card driver, because the SD card only provides storage of raw bytes. But we want to talk to a file system. We want to pull files off and read them or write them or whatever. So that's the layer above, right? And at that point, it's not really a driver at that point. It's a layer that's built on top of a driver, because you're not actually, at that point, you're not like sending signals to a device, you're actually talking at a higher level. So I don't think I would call it a driver at that point. I don't know what the correct terminology would be, but that's kind of how I would think about it. Alright, so we're going to initialize the device, and if I zip back, well actually there's something we need to do, right? So we need to power the device on. So we need to provide power to the device, and we can do that by calling SPI set power, and power is given as a logic level, so logic level high. We set the power to high. So we're turning on the device, apply power, and the other thing we're going to do is we're going to use this mode that the bus pirate has built in. So in this diagram, if we go back to the web page, you see we had to give this pull-up resistor. Well, I haven't put the pull-up resistor in the hardware, in the breadboard that I've made, at least not on the bus pirate side, because the bus pirate has built-in controllable pull-up resistors. So we can actually do that from here. We can say await this.spi.set pullups, and that will be logic level high, and then we can turn the pull-ups on. So at that point we've got the wires like ready to start speaking, and we need to figure out like how we do the communication. And I think this is a good moment to just take a small divergence to like how SPI works, like what's the physical like signaling, how does this look? So we've got these 4 wires, right? We've got this what's called the chip select. I'm gonna write these out like we've got the chip select, we have got the clock, we have got the meso, which is main in, subordinate out, so like bus pirate sending device. So this is this is the device sending, and then we have mosey, which is main out, subordinate in. So this is bus pirate sending. Alright, so these are going to be our signals, and let me see how painful it is to try and draw these wires. So chip select is what's called an active low signal, which means that by default it's like it's running at 5 volts, or not 5 volts. It's absolutely not running at 5 volts in this case. It's running at 3.3. So that starts off kind of high. I'm trying to think how it's going to be the best way to draw this. We'll see it in a second. Then we're going to have the clock, and the clock is kind of like something that goes up and down like over time. Oh, this is not going to work. Grab. Alright, we need one more. Sorry, I should have done some amount of preparation for this. So at least we can just do this now. So the clock goes up and down like this, and I'm realizing that this is not quite going to work, so we'll spread them out a little bit. The clock goes from high to low, and it's kind of like the beat, the drum beat that the whole system is looking at, right? So like every time the clock goes up and down, the device can say, oh, okay, I should do something when the clock goes from low to high, or when the clock goes from high to low. It's going to have an idea about when it should do something. And then when we're sending data, basically what we can do, and by the way, the clock, like when you're not sending data, so most of the time you're not sending data. When you're not sending data, the clock is just either just sitting low or sitting high. So like for instance here, well, that's a weird example. So let's take this example, like the clock is just low until we bring chip select low, which is confusingly, so yeah, SD card, if you run it in the native mode, and actually also in the SPI mode, but in the native mode at high frequency, SD can actually do 1.8 volt. But by default, when you run SPI mode, you're not running at like high frequency, you're actually running at quite low frequencies, and then you use 3.3. And some SD cards have the ability over SPI mode to drop down to 1.8, and it's actually, we'll see that it's something we can ask the device's capabilities, like can you signal at 1.8 volts? I think most devices can't, like most regular SD card devices aren't going to do 1.8 signaling at SPI mode, but they probably will do it natively. So, I mean, I don't know that for sure, but that's the feeling I've gotten from the research I've done. Because I think most of the time when you're doing SPI mode SD card stuff, you're doing it in kind of like underpowered microcontrollers. So here, chip select is active low. So what we do is we pull the line low, and then we can start the clock and we can start sending data. So let's imagine our device. It kind of doesn't matter if you saying you are like high or low. As soon as the clock starts, that's when you start sending data. So most of the time, I'm trying to remember, you can configure all of this stuff in SPI, but most of the time, or the default setting, the data is captured when the clock goes from high to low, and then it's actually captured in the middle of the clock, and that's on both the sender and the receiver. I know that this discussion now is a little bit like low level, like literally, because we're talking about electrical lines, but this is kind of it's going to become important, because unlike the last video where we were just doing SPI transfers, so just sending data, just receiving it, we actually need to control a lot more like directly the signals here, because the SD card protocol wants us to like keep some lines open while we send data and then change them and send a bunch of stuff. So we need to take account for that. All right, so, and then yeah, so you can imagine I'm just going to try and like set up some data here so you can see what kind of how this would kind of look. And let's take those and that, and let's just extend that out. And so, okay, so if we were to see this picture, right, chip select goes low. This is time, obviously, in this direction. So chip select goes low, which is active, that active low. Then we start pulsing the clock, and we're sending data at this moment, right? And in SPI, you're both always sending and receiving data at the same time. It's what's called full duplex, but normally when you're sending data, you don't expect to be receiving valid data. You just expect to be receiving noise. And only when you, like normally what happens is the main device will send a command, and the subordinate device will wait until that command's done and then send its own stuff. But the main device controls the clock, so it's the responsibility of the main device to keep the clock running so that the data can come through. Okay, so the main device, let's try and look kind of how this would be. So when the clock goes from high to low is when we are checking the data. So here, at this point, clock goes from high to low, we check in the middle of the frame, and this would be a 0. And then again, we go from high to low, we check again, this one would be a 1. And clock goes from high to low, this one would be a 0, high to low, 0. So we would be looking here 0, 1, 0, 0. And typically in SPI we send 8 bits at a time, bytes. We're definitely going to be sending bytes at a time. And basically you can imagine that the same thing is happening with this kind of signal line on the well, this is the device sending, but I guess let's just swap those around, say that that's the bus pyro device. You can imagine that on the subordinate device this same stuff is happening, and when you're done with the transaction, so to speak, you will basically disengage your chip select line, and that is kind of a signal to the subordinate device that you don't care about anything else that they have to say. You're done with that device now. So that's that. That is kind of the electrical part of how SPI works, and I hope that made some sense. We don't need to go too detailed with it, but it's good to have that basis. Alright, so in order for us to get into SPI mode, let's read a little bit of stuff here. So power on or card insertion after supply voltage reached above 2.2 volts. So there's a threshold. It doesn't actually have to get all the way to 3.3, but when it hits 2.2, we wait for 1 millisecond at least. Okay, let's put that in the code already. I actually wrote a delay function when we did our flash memory chip, so let's copy that. Let's bring that in, and so we have to wait for at least 1 millisecond, and well, this is actually not really needed for this, because when we're doing this communication with the computer and the bus pyro, there are actually, in terms of what the SD card sees, there are huge delays in time. Like there are huge like gulfs of time where it's waiting for stuff to happen, and we'll see that later if we plug in the logic analyzer. So I'm just looking at the comments here. Dragshot says, fascinating, the seemingly contraptions that pile on top of each other in order to get more sophisticated things done. That is so true. That's such a good way of putting it, because like if you think about how technology works like under the hood, and we're going to see this in a bit with the SD card as well, because there's something buried in how the SD card works, and especially like when it comes to the fat file system, that's so funny in my eyes. I think it's a really funny, like, what you'll find is that throughout the software and hardware stack, you'll have modern devices that are pretending they're actually crazy ancient technology. And that happens all the time. Like, you'll have bits of hardware that are like going through different levels of abstraction. If you start thinking about USB, USB, for instance, you've got the ports. Your USB is connected to like the PCI Express port, probably, if you've got a new laptop or a new computer. So you're probably talking over PCI Express. But older hardware could maybe be talking over just PCI, not even PCI Express. And then you had other kinds of hardware bus protocols that would be connected to, the chipset that talked to the CPU. And what you find sometimes is that older computers, they would stack these on top of each other. So you'd have like, maybe you've got a PCI with like some PCI Express bridge, and then you would have USB going out to that. So you've got kind of these multiple levels. It goes on. I'm getting yeah, it's abstracted all the way down, absolutely, and all the way up. Like it's amazing, and that's well, yeah, we're gonna see some more of that. I won't get too stuck in the weeds with that for now. So we've waited our 1 millisecond, which we basically don't need to do, but we'll do it anyway. We need to set the SPI clock rate between 100 kilohertz and 400 kilohertz. Okay, we can do that. We've got the ability to do that within our driver code. So let's say set the clock rate. So we'll do await this.spy set what's this? I think it's set speed. Yeah, I should maybe call it set clock speed. Set speed, so then we need to provide an SPI speed, and we need to provide between 100 and 400. And we have here the ability to provide a bunch of different things, but 250 kilohertz is kind of in the middle of those values, and it's kind of the best bit. So let's put 250 kilohertz, not particularly fast, but you know, fast enough. Alright, so, and for a reference of what that kind of means, 250 kilohertz, that means that if we have a clock going up and down, that can change from high to low 250,000 times per second. So actually it sounds like a lot, but when you start talking about megahertz and gigahertz, you know, it starts to seem a lot less. And we can talk SPI in even with the bus pirate, we can talk SPI in the megahertz. So it's pretty slow in comparison, but still pretty fast when you think about it. Alright, so let's go back. We've set our speed up. Yep. Set DI, so that's data in, and chip select high and apply 74 clock pulses. DI. That's data into the device. They use different names for the signals here, but data in is referring from the device's point of view. So we can talk about that being the Mosey line. So we're going to set Mosey high and apply 74 or more clock pulses to the clock. The card will enter its native operating mode and be ready to accept a native command. Okay, so this is the first piece of interesting device interaction we need to do. And notice that we actually have to control the chip select line manually here. And this is why I tried to explain the signals, because normally, like in the last episodes, we didn't have to do that. In this one, we actually have to control the lines. And so the fact is we're going to end up putting the chip select line high, which means not active, right? So we're not sending clock pulses while the chip is active. We're just sending clock pulses to get it into its mode. So that's kind of an interesting side note. Alright, so what we're going to do here is we are going to await this.spy.setCS, set the chip select, we set it to a logic level, we're going to set it high, because that's what we have to do here. So we set logic level high, and then we need to send 74 clock pulses. So 74, we can send 8 clock pulses per transfer. That's the best we can do. We can only ever send 8 clock pulses at a time, because that's the level of control we have at the bus pirate. So 74 divided by 8, that's 9.25, which means we need to send 10 transfers. So the way we can do that is we can say, well, yeah, just for let I. This is one way you can do it. For let I equals 0, I is less than 10, I plus plus, await this.spy.transfer, and now we're going to transfer data, and it said that the data in of the device, so the main out subordinate in, that has to be high, so we need to send FF, like a byte where on every clock pulse, we're sending a 1, right? So we send at this point, send at least 74 clock pulses. That's what we're doing. Set CS high. And actually, I've written an abstraction on top of this because it's difficult to kind of wrap your mind around the fact that CS is active low. So when you set something high, you're actually disabling it. So I've actually got something in here which is set SPI, and it's going to be set CS, or sorry, rather, what we're going to say at this point is disable chip select. Chip select disable. And I'm going to use chip select disable and chip select enable instead, because I find it just an easier way of thinking about it for myself. But yeah, when you're thinking about what's happening on the electrical lines, what we're doing is we're pulling it high. Alright, so we send our 74 clock pulses. Then the device should be in the right mode. It should be, yeah, it should be kind of ready. So what we can do is send a command 0 with CS low. So at this point we're doing a transfer, right? We're just doing a regular transfer. This means enable chip select, and we're sending command 0. Well, at this point you might say, what is command 0? And, you know, what does that mean in terms of sending? Because we have this table, but there's no value here. There's nothing here. And this is the point in the process where I tell you that, of course, this isn't the only resource I used while I was building this. One of the really amazing code references that I used, and I tried to use it as little as possible, but I've dipped into it here and there, is the Adafruit Arduino library for the SD module. So Adafruit, of course, they've written this. I think this was literally written by Lemur Fried herself. Not this part, but the SD-Card.h. William Greeman. I guess not. She definitely wrote some of this library. But in here, there are, somewhere in this library, there are a bunch of constants with the command names. Yes, here. And we can just like copy these into the file. I think it's a really useful thing, and this is actually what I did when I was messing around with this. So let's just take that, go up to the top of the file here, paste those in, and they're not going to be, this is not valid yet, but it's amazingly, the only thing we need to do, and this is funny because this is C++ code, and what this is saying is it's an unsigned 8-bit integer that's constant called CMD, and this is the value. And amazingly, this becomes valid JavaScript if we just strip off these uint8t declarations. This is now valid JavaScript. It's kind of, or TypeScript. It's amazing that that just happened. And it's funny because the const keyword means something completely different in C and C++. It literally means like this value won't change, and in the case of microcontrollers, it means that, you know, the microcontroller, the compiler can do special things like, oh, I won't actually make space in memory for this because the value's not going to change, so I can just use the value instead. So it's a good way of just making like a well-defined, well-typed name. I don't like the fact that they've used a capital X here, so I'm just going to change that. I'll leave all the comments in place because why not? But yeah, now we've got command 0, command 8, command 9, blah blah blah, and a bunch of these are all, yeah, so these are all the commands, and we're going to need the responses as well in a minute, but we'll get to that. So the first thing I'm going to do at this point is that when we send a command, oh sorry, yeah, I'm not showing you the editor. I really apologize for that. I'm so sorry. I'm so bad at streaming. Anyway, so all I did was paste in that C++ code and remove the uint8t, and then we'll end up with some valid TypeScript, which just defines all of these numbers. Thank you for poking me on that. All right, so I'm gonna write a send command method. Because we're gonna be sending quite a lot of commands, and it's gonna be like the basis of how we work with this hardware. So obviously we're gonna have a command, and I want this to be like strongly typed. So I'm actually going to copy all of these. Well, I can do this faster like this. I'm gonna copy all these type names, or sorry, these constant names. And then I'm going to make a type from it. So the type is going to be SD-Card, SD command. And what I'm just going to say is that these names are actually like a well-typed, strongly typed. Oh yeah, and I have to use type of here. So now we actually have a type that is like specific for each of these commands. So we can use these names, and we can make sure that if we pass anything else to this method, that it would not be valid. So we're going to have the command, which is going to be an SD card or an SD command. We're also going to need to pass an argument, which we'll take a look at in a second. So that's going to be a number. And let's go back to the amazing page from Elmchan and take a look at that command frame picture again. So when we send a command, what we actually do is we send 0, 1, and then the index of the command. So that's just all of those values that we just brought in. Exploit says also, is this Lua C or just Lua? No, it's TypeScript. And yeah, I see you've said also it's TypeScript, Carol. So yeah, it's TypeScript. So that's what we send. We send 1 byte here, which is 0, 1, and then the name of the command, or not the name, but the value of the command. And then we send 4 bytes, which represent an argument. So if we need to pass like some, configuration to this command, then that's what we're going to do. So we've got those 4 bytes there. Then we have a CRC byte. So it's 7 bits. 7-bit CRC. And we have this thing here, which is the stop bit. So we have to send this 1 here. And then there's some amount of time, and then we get a response from the command. So we won't handle the response part. We're only going to handle sending the command, and because there's different kinds of responses, we're going to have that be a separate thing. So with that in mind, when we go to do this send command, what we're going to want to do is, we're going to have this CRC thing, and no, we'll talk about that in a second. The basis of what we're going to do is we're going to be doing an SPI transfer. And that's going to be sending some data. So we're going to send the command. Then we need to send the argument. And the argument is 4 bytes. The argument is 4 bytes. And we need to send it in big endian order. Which means if you have the number like 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal, when you send it in big endian, you split these up into bytes, right? So we split this into these bytes, and you send the big end of the number first. So this is the big end of the number, right? This represents the biggest part, and then this is the next bit, and this is the smallest part, just like in regular decimal numbers. And yeah, so that means we would literally send the byte 12, 34, these are hex numbers, 56 and 78. So that's that. So I'm thinking I'm just going to do this directly. I'm going to write an A0, which is going to be our argument 0 byte. We always send 4 bytes, so we know we can do that. And the way we're going to isolate those parts, and I've done this a lot of times on this channel, but just so we're all familiar, we're going to take the argument, we're going to isolate the top byte there by ANDing with FF, and that's going to select all the bits in the top byte of this 4 byte number. And then we're going to shift that 1 byte down by 24 bits. And that's going to mean that we have that 1 byte just down here ready for us to use. Will this be available offline? I'm not sure by what you mean by offline. The video will go on YouTube after this, so there will be a recording of this. And as well, sometime soon, I'm going to publish the Bus Pirate code, like the library code. I haven't done it yet, just mainly because mainly because no one's asked yet, and I've just been working on it, right? It's not complete yet. I haven't implemented all the protocols I want to implement, but I will put the code online soon. So yeah, this will be available. So we're just going to continue in this way to isolate each successive byte and shift it down by the amount that it's needed in order to isolate the byte itself. So basically what we're doing is we're taking a big number and splitting it up into small numbers just by isolating and shifting. Masking and shifting, that's what we're doing here. Alright, so now we have the 4 bytes for our arguments. We've got A0, A1, A2, and A3. We'll send those. And then we need to send a CRC. And the CRC is a tricky thing, right? If you don't know what a CRC is, well, I'm not going to be able to explain it here because it's actually something relatively complex idea mathematically. Like it's some quite if you get deep into it, it's some quite advanced mathematics that involves yeah, I'm not even going to get into it, but it involves some kind of abstract algebra and some really interesting kind of polynomial expressions that you can use in order to build error checking into your data transmission. But it's a way of checking that your data is valid when you've received it, right? You get some data and you take the CRC and you compute the CRC from the data you received and you check they match. And actually CRC has this very cool property that it can give you some information about like either where errors occurred or how many errors occurred. It's pretty cool. But yeah, I'm not going to build all that CRC logic here, but we do need to send something. So if we look at this diagram, the byte that we need to send for the CRC, well, it ends in 1. So like whatever we send, it needs to end in 1. And kind of the long story short of this whole thing is that for the most part, the SD card isn't going to check the CRC, so we can send whatever we want for the most part. But that's not true for 2 commands. There are 2 commands that for some reason, and I don't know why, and I would love to know why, but I don't know why, for some reason there's 2 commands where you have to send the accurate CRC. So in that case, what you can do is, because the argument doesn't change that much, you can just use a pre-computed CRC, and that's what we're going to do. So for that, I'll quickly show you. If we go back to the Adafruit code for the Adafruit SD card thing, I need to figure out where it is. I think it's in SD2 SD2card.cpp, and I believe there should be a so we've got SD2card init, and when we do initialization, there's a bunch of stuff that happens, and then eventually there is this wait, no, I tell you where it is. It's in the method that's like send command. This is not like that relevant, by the way. Is it send? Is it just command? Like, what's the name of this thing? Card command. That's what it is. Yeah, there is this piece of code, send CRC. If the command is command 0, then we're going to send the CRC 87. Hey Nate, how are you doing? And Max also, how are you doing? It's not linking. I don't know what you mean by linking. Yeah, so we're going to take these 2 CRC values. So basically, if we send a command 0, we're going to just send a CRC of 95 hex. And we don't need to care because like we always send the same argument. So that is the valid CRC. So that is what we're going to do in our code. So we need, I'll just copy the C++ and we'll translate it here. So if our command is equal to command 0, then our CRC is 95. Correct CRC for command 0 with arg0. And otherwise, and I just want to put that on one line actually, just to do that. And if our command is command 8, then our CRC is going to be x87, which is the correct CRC for command 8 with with argument 1AA. YouTube wasn't turning into a hyperlink, not a big deal. Ah, okay. In the Discord, you mean? Yeah, I'm not sure about that. I used like YouTube's short URL, and like I found that in a lot of places the short URL doesn't work properly. Like it doesn't show a preview window and all of that kind of stuff. All right, so now we have a correct CRC because if we send these two commands, then this is a valid CRC. If we send any other command, the SD card doesn't check. So we're in a good place. And that's basically it. I think that is our whole method, which means we don't really need to have this thing be async. We can just return the promise. And yeah, that's pretty good. So bringing this all the way back. Oh wait, there is one thing, and this is really important. This is really important. By default, and maybe I'm going to make this explicit in the library. This is part of the reason I haven't published the Bus Pirate library yet, is I haven't made all of these little decisions. But when you do a transfer, you'll notice that there are a couple of different arguments. So there is a transfer data, which is where we put our data that we're going to transfer. And there is a second one called chip select control. And chip select control, we're going to provide an argument here, and we're going to say that our chip select control is manual. Because by default, the chip select control is automatic, which means that when we do a transfer, the library takes care of setting the chip select signal, making it enabled for the time of the transfer, and then disabling it at the end. And kind of because of the way this works and the fact that we're going to want to wait for a response, and we don't know how long the response is going to take to get back to us because that varies from SD card to SD card, we're actually going to want to keep our chip select signal enabled for possibly a long time that we don't know. Like we don't know the number of bytes that we're going to have to send in order to keep it open. So we want to have manual control of that. Alright, so at this point, now we can actually do the first send. We can send command cmd0. So cmd0, going back to this page, cmd0 is go to idle state. That's kind of what it means, and it's a software reset. It's us telling the SD card to kind of reset itself, like clear out any values it had, whatever. Get into a state where we can start talking to it. There is actually a really useful diagram from this website, and I don't know why they didn't put it on the main page, but there's like there's this link, and you have to open this link in order to see this diagram. I don't know why they did that. But this diagram explains this really well, this whole process. So actually, let's just start looking from here, and I'm going to zoom into this a bit. So we're here now. We're sending our command 0, and this is one of the cards which our CRC must be correct for. And yeah, so we're going to send that. And in order for us to send command 0, which is software reset, we first need to enable chip select, which is going to be a manual thing. And what I like to do is I like to write the corresponding disable immediately so that I don't forget to do it. That's kind of like if you're working in a language where you have to control your memory and you do a malloc, for instance, like immediately writing the free and making sure that you actually do that somewhere. Or in some of these newer cool languages where you can do defer and stuff like that. So that is basically the equivalent of this. And And then we're going to do await this.spy. No, not this.spy. This is going to be our first abstracted thing. This is going to be our send command. I think I'm going to rename that to SD send command. So it's like clear that it's an SD card command. Oh, lost it. All right, so the command we're going to send is command 0 and the argument is 0. All right, and now we are, oh God, I'm so sorry. So yeah, what you missed there was was that I wrote these 2 lines of code, or these 4 lines of code. So chip select enable, chip select disable. So that's the corresponding thing that I was talking about. And then we're sending command 0. And now we need to await the response. So I actually need to zip back over to the thing, and I will try really hard to remember to switch the window afterwards. When we send a command, so we send this command, and then there is this thing called NCR, and this is described somewhere, and I think it's here. So the response is sent back within the command response time, which for some reason is called NCR. And it's 0 to 8 bytes for SDC, which is a type of SD card, and 1 to 8 bytes for MMC, which is like the technology that these are kind of both based on. So we don't know how long it's going to be for this SD card. It's implementation specific, so it could be anywhere from like the very next byte to 8 bytes later, but it should be within 8 bytes, so that's kind of something to keep in mind. So how we can do this is we can write a method, and this is going to be an async method, and let's call it SD await response. And what this is going to do is going to be a method that we can call. We can await this thing. Yep, not seeing. Oh, I did switch this time. Good. We're going to be basically like checking to see if we're getting a response. And we know that we're not getting a response if they send us, if we get back FF. This is something really nice that we'll see. Here is the data out. So this is what the device sends back. The device is always sending ones. It's sending FF in terms of a byte all the time up until the point that we get a valid response. And then we get something different. And the nice thing is, and they've designed it this way obviously, but you'll see that the response byte, there's only 7 bits in the response, and that is not an accident. It's not like, oh, we have 7 bits, like we only had 7 pieces of information to transmit here. They purposefully chose 7 so that this topmost bit could be a 0, which would mean that you would never ever be in a situation where your response was FF. And I think that's really beautiful. That's the kind of thing you see when you dive into these protocols and you look for the little like gems in these things. Like that's one of those little gems, I think. So we're just going to wait until we get something that is not FF. And we can put a timeout on it so that like we don't end up waiting forever, but like we know that it's going to be there within 8 bytes. We're speaking over a 250 kilohertz line, so 8 bytes, not going to be very long. We don't really need a timeout. We could just check 8 times, but let's just put a little timeout. So timeout in milliseconds, we'll say we'll wait maximum 1 second. 1 second, 250,000 bytes are going to transpire in that time if on the best case. So it's a bit of overkill, but it'll do. All right, so what do we say? Like we started this whole process at this point, and then we're just going to loop until we get the byte. In order to get a byte, we can do, so this is going to be our response. That's going to be await this dot spy dot transfer. because when you transfer, it's full duplex, remember? So when we send something, we're also receiving something at the same time. So the SD card, it tells us on this page somewhere, and I don't remember it because I didn't read this whole page through on the stream, but here it is. Because a transfer is driven by a serial clock generated by host controller, the host controller must continue to read data and send an FF to get a received byte. I think that is actually a hard requirement. I think you have to send FF. If you don't send FF, I think weird stuff happens. Like you end up getting corrupted data on the line. And that is something I saw in the last couple of days when I've been playing around with this. I was sending 00 because I thought, oh, it can't matter. It matters. And yeah, that's one of those fun things you get with playing with hardware. You don't get errors, you just get corrupted data. And you're not sure if like the data is actually corrupted or if you did something wrong. Most of the time you did something wrong. So we have to send FF. Then we can just check, is our response... If our response is not equal to FF, well, that means we got something that's valid, so we'll return the response. And otherwise, oh, it's a buffer. So, like, we're getting a buffer. It's going to be a buffer with one item in it, so we need to check that. So I'm actually going to return the 1 byte as well. You get as many bytes back as you transfer. So in this case, we know we're getting 1 byte back. And then what we can say is, well, we need to pause for some amount of time because, well, this is like if we were writing this in C or C++, we wouldn't have to put a delay in here. But because we're writing in TypeScript and ostensibly in JavaScript, there's something called the event loop. We need to allow like events to come into our program, so we can't just block in a while loop. We need to actually introduce some way of like delaying for a moment. So we're gonna add a delay of 1 millisecond, which is a lifetime on terms of this this line, and we're going to say if if date.now, so like check the current time like in milliseconds, if that minus the start time, if that's greater than our timeout duration, then, well, in that case, we'll throw an error. Throw new error. Didn't get a response in time. That's it. That's how we're going to await a byte. Edward, bro, your content really inspires me to delve into the world of low-level programming. I'm really glad you're inspired, Edward. Truly, that is exactly why I do this channel. So we are going to, at this point, and we want to get the response. And the response should be something called R1, right? That's what this is called. So we're going to get R1, and the way we do that is SD await response. We'll use the default timeout of 1,000 milliseconds, an eternity. And then we should get this R1. And let's, before we do anything else, let's actually take a moment here and just log out what happens at this point, because by this point we should see something happen. So I'm just going to console log R1. And this is going to tell us very quickly if we did something wrong or not. Because if the device is like dead and it's not doing anything, we're just going to see FF because we have pull-ups on the line. Otherwise, we should see something interesting. So I'm going to plug in the device to my weird setup, which you can't see here, but I showed in the beginning. I have an insane like wiring setup here in order for us to maybe do some logic analysis later. I've plugged in the bus pirate. I'm going to clear the terminal and I'm going to run ts node yeah, it's true, right? 1,000 milliseconds, like, you know, that's your whole time budget for yeah, if you're trying to do something vital and you have to wait a second. If your car waits a second before it, gives gas, you feel that. All right, so running the driver. And of course nothing happens because I wrote the class and I didn't call any of its methods or make an instance of it, so of course that was anticlimactic. Let's make a main async function. And inside that we'll create an SD card, so that's going to be a new SD card. And we need to pass a SPI interface to that because I talked about this whole thing with with dependency injection. So we're going to make a new SPI mode. And to that we need to pass the device path, which is the USB interface that we're going to talk to for the bus pirate. That is on my computer, dev tty USB 0. And it probably will be on yours too if you use Linux. And then we're going to pass SPI to that, so we inject our dependency. And later on, if we were going to do some testing, we could make an interface for the SD card and the SPI and blah blah blah, and we could do some testing without actually having to have the hardware connected. And now, so then we're going to do await sd.init, and we can do, and that's it. That's all we need to do actually, because we're doing all of this in the init method. So then we can just call main. Let's run the driver again. Keeping my eyes on the lights, I see that some data has been sent, and we didn't get a response in time. That is an interesting one. So let me see that I wired this up correctly. It looks alright. I think let me have a think here. So we do an SPI transfer with manual chip select. We're awaiting a response. We do another transfer of FF. We get a response. All right. So debugging time. I won't spend too long on this. I've got a working set of code, so I can actually go and check. I can check against my working code to see what I've done wrong here. But let's just print out the the responses we get in the meantime. Yep. So we got a bunch of FF, and it looks to me like we got more than 8 FFs. So I'm pretty sure that it's just not working at this point. So we probably, I know what I did wrong. I actually know exactly what I did wrong. I did this the first time I wrote this code as well. And that is that when you send a command, let's go back to the amazing resource here. When you send a command, it's not just the command index. You actually have to send like hex 40 ORed with the index, right? So the top 2 bits of the byte need to be 0, 1, which means we can fix this, I hope, I really hope it's this, by basically ORing hex 40 with our command. Let's try that. We'll leave the console logs in. Hey, look at that. All right, so you can see here that it was only 2 iterations of the loop until we got a response. So we had 1 iteration where we sent a byte and nothing came back yet. And then immediately after that, we got a response. So we get a response within 1 byte. That's not too bad. And we got the number 1. Is that correct or not? We will see. And I was a bit optimistic with the whole FAT32 file system layout. I don't think we're gonna get to that on this episode. So if you're tuning in this week and you're enjoying it, well, we'll continue this next week, and we will get deep into the FAT32 file system stuff as well. But we need to do all the physical SD card interaction first. So if we go back to this this page and we look at what happens during this initialization process. We send command 0 and it should be received successfully if CS signal is low, which means active. The card enters SPI mode and responds with R1 with the idle bit set, which is 1. And we saw that we got 1. So that means with reasonable confidence that we are now talking to the SD card properly, and we're doing it in this, like, you know, very low level, very like controlling the SPI interface kind of way, which is really nice. Great. Where do we go from here? So when we've sent command 0, let's have a look at this thing. So did we get R1 response? No error, unknown card, power off. All right, let's actually implement that. Let's check for an error and let's implement error power off. So instead of just console logging R1 at this point, what we can do is we can check, hey, is R1 equal to 0x01? Instead of using 0x01, I actually want to grab all the constants, and we can go back to Adafruit for those. SD-info, so these are all the SD card commands, and these are all the responses. So let's grab the responses, go back to the code, and dump in these responses, get rid of the uint8 T's, and yeah, the beautiful thing again, get rid of those. This becomes valid JavaScript and TypeScript, although I don't like the capital OX, so I'm going to get rid of that. That shouldn't bother me as much as it does, but it for some reason really does. And so the R1 ready state, that's when there's nothing. The R1 idle state is when there's a 1. So we can actually give that a name now and use the name. So if R1 equals the R1 idle state, or I guess if it doesn't equal the R1 idle state, let's say at that point, await this.spy.setPower logic level low, turn off the power, and throw new error. Did not get the expected response from SD card during init. We could give more details here, and in fact let's give some more details here. Let's actually show what R1 we got. This is what we received in that case. Okay, so yeah, Max is saying that he agrees with the OX thing, and yeah, it's, I don't know what they were thinking when they wrote that. I mean, it's like, you know, how can you ever trust someone after they display those sort of psychopathic ways of doing things? Sean Paulson also said, love your videos, man. Your last video posted about priority queue came in very handy. Just so happened to have needed it the very next day for some GIS work, making a flight tracking map. So thanks. You're welcome. I'm really glad also to hear that you used it for a purpose that wasn't just a school assignment, because, you know, that's often what you hear when you're like, oh, I did this, I learned about this cool data structure. Oh, I ended up using it in my computer science homework. But it's really cool to hear that you used it. Did you have some sort of like RTOS or something, and you were doing like priority stuff there? Like you had to do prioritization on queues and stuff like that? I'm interested to know what your application was there. All right, let's get back to the initialization process. So now we're going to want to send command 8, and we're going to send it with 1AA. So everyone in the world uses this like 1AA situation, because as you will see with what 1AA actually means, the AA part is just sort of like you have to invent a byte. You can send any byte you want. And everyone uses AA because everyone has the pre-computed CRC. No one's like computing CRCs from scratch in their SD card implementations. So everyone uses all right, let's actually see what Command 8 is. Command 8, according to this, is send if condition, which is for SDC version 2, check the voltage range. So what we're going to do is we're going to check which voltages are allowed on this card. And someone asked a question earlier in the chat about if because I mentioned the SD card works on 3.3 volts, and someone mentioned not 1.8 volts. Well, this is where you can actually ask what the SD card is capable of, and you can actually then start talking it into putting itself into different kinds of situations. So in order to just like, there's more context around all of these things, right? Even in this website, which is a great resource, like that's not the end of the story. And in order to just show you that there is more like meaty detail out there, I'm going to copy in documents, datasheets, SD physical layer spec, and we'll put that here in the SD directory. And there is this SD specifications part 1 physical layer simplified specification version 8, which actually was updated as little as 2020 ago. So this comes from the SD card association. You have to go to their website to download this, and in order to download this PDF document, you have to sign an agreement, or you have to click an agree button to some legalese, which is just to read the document you have to agree to something, which felt like a little bit too much, a little bit too much for me. Well, not too much because I clearly did it, but yeah, in here, basically, this document goes into quite some detail with what this means. And if I like search for like Command 8, for instance, this is probably going to be really slow because this is not a native. Let's see if we can find where it talks about Command 8. Oh wow, it even searches in the images here. This is quite a nice document, by the way. This is not like a shoddily put together thing. This has a lot of like nice, a lot of nice diagrams. It goes into quite a lot of detail. But what I want to see is like, what I want to see is like kind of what the voltage ranges are, because so here we ask about. It's mandatory for the host compliant to the physical spec to send command 8 before it sends a command 41. So like this is just telling us that we need to do these things. Like I'm not like going for spec compliance or in any way, like for my application, I really want, one of the things that I want is the most minimal implementation I can get away with in order to like read and write to the SD card. So I'm not worried about like the most generic thing. So I know somewhere there is a really nice thing with a table. Yes, this one I'm looking for. So basically, this is when we talk, when we send this send interface condition command is defined to initialize SD memory cards compliant to the physical layer specification. It's valid when the card's in an idle state. It does a voltage check, and it enables expansion of existing command response, blah, blah. A bunch of this is actually the same commands are used for both like the very simple SPI mode, like the primitive mode that we're talking to the card in, and like the later, like more native modes that the SD card speaks, which are able to go at very high signaling rates and that kind of thing. You know, when you've got these SDXC cards that go into like video cameras and are able to capture trillions of bytes per second, you know, like they're still using the same set of commands. They still have to ask all of these kind of things. Like Okay, so we end up sending our command index. We send some reserved bits, apparently. We ask about PCI Express 1.2 volt support. So it wasn't 1.8 volt, it was 1.2. So it can run at 1.2. Then there's a whole bunch of stuff. And then eventually, like when we're asking about like supplying a check pattern and stuff, like the only thing we're really asking about is this 2.7 to 3.6 volt range. Like that's all we really care about. I just wanted to bring that in just to give a little bit of like background context about like there is more detailed information, and when you're like struggling with something, like sometimes often, just go directly to the source, like the data sheet or the specification. But sometimes specifications, like, they contain all the information. That's their job, right? They have all the information. And sometimes when you're first trying to get to grips with a system, you don't want all the information at once. You kind of want to see the broad strokes. And then reading other people's implementation code and summary pages like the one that we're looking at here, that is quite a good way of doing it. So we need to send this command 8, and we need to send an argument, and the argument is going to be the supply voltage and check pattern. And so when you actually and so what it's showing, right, is that we need to send a bunch of bit patterns, and this is what we saw in the spec as well. We need to send some bits that like talk about the supply voltage, some bits that talk about the check pattern, blah blah blah. Like when you put all of this out, the supply voltage part ends up being 0001, and the check pattern ends up being AA, right? Because like we can choose the check pattern, but we end up picking AA, which means that if you write that out and everything else above that, right, the RSV part, that's all zeros, that's reserved, and you have to put zeros in. So the end result of that is that you send all zeros, 1 AA, right? That's what we end up sending. So that's where that 1 AA comes from. I think it's quite good to, if you see these magic numbers, it's good to figure out like what they mean and where they come from. Otherwise, they're really like magic numbers. You're basically, you're performing an incantation and stuff happens. All right, so at this point, we're going to do some more stuff. So let's make a pair of those. Back in the code. You didn't miss much. I just put chip select enable, chip select disable here. And we're going to send another command. So we're going to send this time, send command 8. And we send that with OX1AA. And yeah, we're going to get a response from that. And so what I typically do when I'm writing an SD card driver, what I did in my previous implementation is that I made R1 a mutable variable, because you often need to get an R1 response, so you might as well just get the same one over and over again. So then we can say R1 is equal to this dot SD await response, and really nicely we get a type error here because this is going to say, hey, you can't assign promise of number to number. That's why I love TypeScript, because it lets me know I missed the await keyword there. So so we're going to get this response, but we don't only get this response from this command. We actually get for this we get an R7 response. So what's R7? So it doesn't actually, nothing mentions it here, but an R7 response is R1 plus a 32-bit return value. So what we're going to do is we're going to get our R1 and then we're going to get our R7. So in order for us to do that, we need to await this dot SPI. Wait, how are we going to do this? It's actually we just need to get the next four bytes. So what we could do, what's going to be the easiest way of doing this? I think what I'm going to do is I'm just going to do a transfer of like, this is just to save time. I would actually make a just like a, you know, in that case I actually am just going to do a quick method here, which is just going to be called SD receive. We're going to receive a number of bytes, and the way that we can do it is we just, in this case we're basically going to do this.spi.transfer, and we'll send the number of bytes that we are interested in. We'll always send FF. So we're going to get back n bytes, and we're sending the right receive thing, and then this, we don't need an async. Yeah, so instead of doing this now, I'll just do this.sdrx, and we'll say 4 bytes. Then we're going to have 4 bytes back, and that is our R7. Alright, and now let's see where we are now at this point. Let's console log R1 and R7, and we'll see kind of what these should be. And we can see kind of what they should be by looking at this website again. So when we send command 8, it's going to say, are the lower 12 bits in R7 are like error or no response? Then we're going to try and do some other stuff. And if those same 12 bits are 1AA, we get a match. That means that this is actually correct. And what it says here is this loop may take 1,000 milliseconds. And I think the loop that they're referring to is this inner loop here, and not this thing going on here. That's a mismatch, and this is where it's not a mismatch. Okay, cool. I hope that's clear. So let's go back. Let's unplug the device, plug it back in again, and run the driver. Okay, so we can see, yeah, I should remove those other console logs, but what we end up getting in the end is we get a response of 1, so that is our R1 idle state, so that's expected, and then we get back 4 bytes, the bottom 12 bits of which are 1AA. So that's great, we actually passed this point. This is how we definitely know that we're talking to the SD card correctly, because there is no way we would get back 1AA on this otherwise. Sorry for bumping the table there. Alright, so we're really on a good path here. I would really like to finish this initialization sequence before we finish. So let's go into the point where we had no mismatch, so we end up going error or no response, or a mismatch, or we go into this part. Okay, so then this is going to be a 1AA. We need to check those conditions, so let's do those quickly. So we can just check R1 again, because it should also be the same, so we didn't get thing. And this is not just during this, is going to be during the power check at this point. And then R7, we would expect that if R7, we're looking at the the second, like this is 4 bytes, right? And we're indexing into the array, so it's like we're looking at the 3rd byte now. If it's not equal to 001 and R7 at the 4th byte is not equal to OXAA, then that's also an error. We'll also shut the power down. And we'll say did not get the expected response from SD card during power check. Yeah, well, we'll leave it for now. It's not the best error message, and actually we could just collapse this. Okay, so yes. So let's go to the next part. Now we have a kind of loop situation going on. So what we have is that we're going to check this a command 41, and we're going to be sending this big long string here, like 40 million bajillion, and we're going to check if we get an R1 response. And until we get an R1 response, sorry, until we get a 0 response, like if we keep getting 0, 1, we're just going to go back to the top of the loop. So this is like this is going to be like one of those interesting times where we're going to need a loop and we're going to have our own timeout. And it actually explicitly says this can take 1,000 milliseconds. So it can take an eternity in this case. Alright, so how are we going to write this? Well, let's just set up the loop first. So let's do a while 1. I'm actually going to mostly copy the code out of our like SD await response, but we can't use it exactly, so we'll make this one custom. We'll have our started. I guess started doesn't need to be a let. And if it takes more than 1,000 milliseconds, let's give it a little longer in our case. Let's give it like 1,100 milliseconds during init. So we'll distinguish that. So what we want is we want to get a response that's actually assigned to R1 in this case. And we're going to say, while R1, we're not going to be doing any returns. We're going to be doing a breaking from the loop. We can't do that because... Sorry, this is ugly code. I mean, I'm not advising anyone to write this kind of code, but I'm just going to do it for now in the interest of time. So if R1, and in this case we want to say, like when R1 is equal to R1 ready state, that's what we're waiting for, the ready state. Then we're going to break. Otherwise, we're just going to keep going. And we're not going to we're not going to be transferring just a random byte here. We're going to be doing a whole command situation. This is a little bit complex. I don't know how I ever thought I was going to get this like all the way to the file system in this video, but eternally optimistic. Okay, so if we go back to this command table, we'll see that this a command 41, it has this asterisk, right? And what that says is when a command n actually means a command sequence, a command 55 and then a command n. So what a command 41 means is we're going to send a command 55, which is a leading command, and then we're going to send a command 41, and command 41 is then this one, which is append opcond. For only SDC, initiate the initialization process. Shouldn't those power check error conditions use some ors rather than ands? I think the reason we're not using ors there is like some nice De Morgan's laws stuff. It's because I'm actually checking the inverse of the condition, right? So I'm saying if it's not the idle state I'm expecting and it's not the 1 byte, and because of that we want to make sure that like we're negating all of those conditions, right? So if any of those conditions end up being true, then we want the whole failure to happen. I do recognize that it's a bit tricky code. These kind of yeah, like deciding how you're going to write these error conditions is always tricky, but I would split this one up into a couple of different error checks anyway. So I'm not saying this is the best way of doing it, but it should identify the correct thing in that case. All right, so what we actually need to do is we're going to send command 55, which is just our app command, leading command. We expect an R1 response from that. We basically don't care what comes back from it, so as long as we get a valid R1, then we can send our command 41. So let's try that. So here, await this.sd send command. Our command is going to be command 55, right? Yes. We don't send an argument with that. I'm pretty sure. I need to go back to the table to look at that. 55, 55, no command, so we send 0. Alright, so that should work, and then we can await this, and then I guess we need to assign R1 this dot SD await response. And again, didn't use await, so we got an error. I love that. Alright, so that's our leading command. Then we need to send the actual command. SD send command. And that's going to be a command 41. And we have to send it with OX40000000. Why do we need to send it with this command? With this argument, the reason is, and I don't know if it mentions it here, here it's recommended. Basically, this ends up being a bit pattern, and you see this if you read the SD specification. But basically, we have to send a bit pattern of stuff here, and the bit that we end up sending there is kind of like a question, which is basically saying like, are you an SDHC or an SDHC or an SDH device? It's basically like, do you have certain mode settings that I could potentially take advantage of? And yeah, it's just a question that we can pose to the SD card. So I'm not going to go too deep into it for now because I'm looking at the time and thinking it's getting on a bit, and I would like to get to the end of this. But then we need to do our little our await loop. So we don't need to do a transfer, we can do an await response. At this point, I don't know why I didn't do an await response in the first place. So then we send the command, we await the response, and if it's the ready state, then we break. Otherwise, we keep trying until we get out of it. So yeah, we need these chip select enable as well, which I didn't put. Chip select disable. One thing I noticed is that you actually don't need to do this in multiple chip selects. Like, you can do all of your communication in one big, like, kind of one command, which is different to how a lot of the other devices I've seen, at least I think, it's at least how I've written the code for them. Yeah, you can actually, I observed that in the Arduino code that they actually do this all in one big chip select active situation. So this is not strictly necessary. You could probably do it once in the beginning and then just change all the settings, but do it like this, it kind of helps me think about it in the right way. Alright, so let's see. At this point, if we can see here in the diagram, if it goes to a timeout, then like we should, at this point, we get an error, no response, or timeout, then it's telling us that we should go into unknown card, power off failed. Yeah, okay, so the previous step is telling us that we should try something different. So yeah, we're just going to go this way. That's actually easier because it just means copy and pasting this nice line here. I guess we're already doing it, and instead of saying didn't get a response during init, we can say didn't get a response during a command 41. No, is it 41? Yeah. Good. If we get to that point, we move to the next part where we have to do command 58. So what is command 58? Command 58 is read OCR. So we need to read the OCR register, and OCR, what does that mean? The OCR register should be read. So the OCR register is the operation conditions register, and it should be read and confirmed during the operating voltage during initialization. So we already have looked at the operating voltage, I believe. Yes, because that's the thing. When you send R7, what you actually get in response is the OCR register, but it wants us to read the OCR register again. I don't think we need to care about the response that much. Let's have a look. If it's rejected, blah, 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 blah. Yeah, so the next part is gonna like the reason I know that this is already an SDHC card is because it's an 8 GB card. So that's basically, it's the high capacity card, so it has to be that. And this is like this says that it's the maximum capacity that you could use for a FAT32 file system. Up to 32 GB, right? So if we were on a 64 GB card, then I guess like stuff would go wrong in FAT32. I'm just trying to see, because I'm now seeing that there's a slightly different thing. Oh, we need to read this command 58, so let's just do it anyway. Let's send it, see what we get. Hey Lions Gamer YouTube _dash. Alright, so we'll initiate another sequence, and it's going to be sending command 58. And we have to send an argument, question mark, we send 0. So we do that, and then I'm zipping back and forth a lot, I'm sorry about that. We're going to get, I think we're going to get what is called an R3 response to that. Let me just double check that. Yeah, we get an R3, which means we get an R1, and then we can receive the OCR. So let's do that. Let's get our R1 response, then let's get our OCR, and we can do that by saying this or await this dot SDRX, and we want to receive 4 bytes. And let's just print the OCR at that point, because I don't remember exactly what's in there. It should, I think it's just going to be 000001AA. Does that make sense? Maybe it doesn't make sense. Let's just see what's in here in any case, and let's see also what's in R1. Make sure it is what we think it should be, and let's also remove the console log from the SD await response, so we don't see all of that stuff clogging up the line. Reset the device, run the driver, and we got an error. Okay, so didn't get a response in time. Line 106. That is quite far back in the process, right? Oh, it's in here. Okay, so it's actually 191. That's too far back, 167. Okay, so that was here. Okay, so that's during A command 41. And this is that thing where it basically said this can take longer than a second, right? So let's put the timeout here, that it should be longer than that. Let's actually give it more time than it seems like it needs. Let's give it 5 seconds. It seems to be using all of those 5 seconds, so I don't think that's going to work. Alright, so what's going on here? Probably I've made a mistake. We send command 55, we get a response. Let's put a log in here. See what R1 comes back with. Wait, something seems wrong here. This isn't right. Yeah. This should be R1. What does SD41 come back? Because we're not even saving the result of it, and I'm pretty sure that's wrong. So command 41 is, okay, so that's where I'm going wrong there. I'm actually expecting more data to come back than actually is. We should be collecting the R1 response there. No, I'm definitely getting it wrong here. Getting myself confused. So this is true. We send the command and then we await the response. So we get a response for that, and then we send 41. Sends the host capacity support and activates the card's initialization process. So we do that, and then we await a response. And it seems that we just never get a response back. Let me double check what's going on here. 41 argument 2. So reserved. Bit 30 is the high capacity report. Okay, so it's literally this one thing you ask, but you have to send 32 bits. So we send that. There's no data coming back on it, and it's for SDC only. Initialization process. I'm going to reference my other implementation and just see what I was doing there. So we send that. Didn't really seem to be doing anything too different there. At least, I don't think. I know you can't see the other implementation. So started, the only thing I think is started on the outside of the loop. Then we do this. Command 55, sending 0, waiting for a response. Sending command 41. 1, 2, 3, 4. Waiting for a response, and I was getting a response within that short amount of time before. So do we just never get it? Because here if I do console log R1, were we seeing any kind of thing before? Because we should see at least one log here. We get 1. Yeah, so it just doesn't respond. It's really strange. That's really strange. I'm trying to think what could be doing differently here. Is it definitely command 55? Leading command. And then a command 41. Yeah, kind of confused by this. Yeah, the code, I mean, I'm not writing any code at the moment. I'm just looking. So so could it be this? What if I just if I don't do that? Oh, because it's actually throwing the error inside this point, right? It's throwing inside SD await response. So let's make sure I wrote this correctly. Let's log out the responses again here. Just took those out, but let's put them back in. And let's remove the log that I had here for now. And reset the device. Run it. Alright, so that was our initialization stuff, and then here we just got to the point where it was taking too long, right? It's not sending anything back. It definitely can take a while. Let's just give it some more time again. Alright, yeah, I mean, it's sending tons and tons of data, and it's really just not getting anything back. So that's kind of confusing. I'm actually just going to copy paste my other piece of code, which basically looks pretty much the same. And we'll see if that behaves differently, and then I don't think it's going to, but right. So differences to the last time apparently are called R1 lowercase r1. Everything else should have the same name. Let's try it out. And if it doesn't work, well, I think we're going to have to call it a day, because we got pretty far, but it seems that something went wrong. Alright, let's run that. Yeah, so this one is also not working. So if this is the case, I guess that I have to have written something differently in send command. Await response. One of those. So maybe I'll take a quick look. See how I wrote await response. Yep. I mean, it doesn't look really any different to what I would have expected. I'm pretty sure it's exactly the same implementation. So what am I doing in send command? Let's make sure that is the same as well. So that is... Oh! Here's one thing I'm definitely doing wrong. Oh my god. Good thing I checked this. Right, so if you remember rightly, when I wrote this SD send command method, we had to provide chip select control manual to this method in order to make sure that the underlying library doesn't take control of the CS signal. But I do a transfer in SDRX, which we're using. Are we using it here? We're using it somewhere, I believe. We're not actually even using it here, but that needs that same chip select control. Response, we should be able to use SDRX here. That's what I was doing in the other one, and then that way we don't need to check character 0, because this should SDRX. Oh wait, we still would need to check 0 because we get a buffer from that. True. I'm trying to think, is that going to make any difference? SDRX, like where are we calling that? We're calling it here on the R7 part, so that would have done some weird stuff. And we are calling it for the OCR, but that's later. So there is some chance that that was the reason. So I'm going to disable the device, run it again. What do you know? That's it. That was the problem. So yeah, that's hardware for you. Like I said, you know, you make one mistake and you just left with the wrong response from the device, and you have to try and figure out why this happened. So yeah, so in this case, the trouble was that the underlying library, and I'm definitely going to change this now because I see how annoying it is if you're working with it. It has a default argument for that transfer function, which says automatic chip select control. And I'm going to force the user to provide that because it's this is how you can avoid that kind of error in your API. So lesson learned. Quite happy with that. I'm glad that we got this running. So you can see that this is the response we get from the this is the response we actually get from the OCR register. So it's this. We have C0FF8000. And kind of, I wonder if we can see just here at a glance what those responses should mean. So we should get a 32-bit return value. The lower 12-bit in the return value is 1AA. So that was just yeah, that means the card is SD version C. Yeah, but that was when we were asking it via the we send Command 8, yeah, but we're not talking about Command 8, we're talking about a Command 41. So do we see the response from this? We keep trying, eventually we get through. And we initiate it, and then we read the OCR. And we check the CCS flag, so that's bit 30. If that bit is set, then the card is a high capacity card. So, okay, so what we're checking there is the 30th bit. So we can do that quite easily, right? What we want to know is if OCR, and we can create a mask to get the 30th bit. We can do that with 40000000. So you're seeing now where those two things come in. And because of a, oh no, we need to, yeah, okay, so we're going to check the first byte, and then we only need to check hex 40. This is one quirk, by the way, and we're really getting to the end here, but this is one little quirk that you can look out for when you're doing this kind of masking operation. If you want to compare the result of this thing, you actually need to parenthesize this side, because this has a lower operator precedence than the equality, so it would actually check if 40 was equal to the thing. So always make sure you do that, because that is a really annoying bug. It stems from C, which kind of got that wrong in the first place. In this case, if this is not the same, right, if it's not OX40, then we would throw an error here saying we only support high capacity cards in this case, right? You could actually support lower capacity cards, but we're just going to say driver only supports SDHC cards. Cool. And then the last thing we would need to do is to send command 16 to force it to work with 512 byte block sizes. And that is something that we will get to when we start like interacting with the file system. And incidentally, we actually don't have to do this, because an SDHC card always works with 512 block 512 byte blocks. These other types of cards, right, SD version 1 and MMC, they can work with variable amounts, but we will always work with 512. So we actually don't need to send command 16. But we could easily do it because we don't actually need to do anything special. So let's just do it just to finish this off and have it finalized. So I'll copy this here. Why don't we just copy that whole block there, because we can throw the error otherwise. So we're going to do one more command. It's going to be command 16. Apparently we don't have command 16 here. Yeah, command 16, is that going to be F? It probably is going to be, let me double check. I think it actually would be the number 16. No, because here command 13 is D. So let's just add one in between, which is command 16, which will be F. And let's add that to our list of valid commands. 16. I didn't write a comment for it now because I'm really just racing against the clock to get it done. And we're going to force this to a 512 byte block. We're going to get our R1 response. And what we can say at this point is that R1 should definitely be, what should R1 be? I think it should be, if it's not equal to this dot, no, not this, R1 ready state, then I think that would be an error. And that would be unable to set 512 block size. If we get to the end of this method and we don't get any errors, probably we're going to have some console logs in here. So let's just get rid of that again. If we get to the end of this method and there are no errors, that means that everything worked correctly, and we have successfully initiated response. Of course. Oh, I should have expected this, right? It is possible. I'm wondering what the response was actually. Let's see. What was R1 at this point? Let's try one more time. It's probably going to be... what is it going to be? Does it mention it here? No. Oh, we shouldn't do this. Oh, this makes sense. We shouldn't do this. If we get a 1 in the CCS, then we should actually just... It's already in block address mode, and we should skip it and not send command 16. So there you go. We shouldn't do it anyway. Let's get rid of it. Let's get rid of command 16 now, because it's not doing anything for us. I'm pretty sure I went through this exact same process when I wrote this the first time again. Like, I also brought it back in and did it. Okay, one more run, and since we errored there, we know it will work, but I just want to, you know, just want the win. And at this point, we can see that literally nothing happened. Shouldn't command 16 be 10 instead of F? It should. It absolutely should. Yeah, I messed up there. Although I was following command 13. Command 13 was D. No, you're right. It should be 10. Completely got that wrong. But in any case, we don't need to do it. And as you can see, the device is now just hanging, and that is because we have an open communication channel with the bus pirate. So at this point, we successfully initialized the SD card. We're ready to start talking to it, extracting data from it, getting bytes and stuff. And that is what we're going to do next week, because this stream has gone on too long already. So I want to say to everyone who is still here, because there's still quite a few of you here, thank you for joining. I really appreciate it. I really appreciate also all the questions and the nudges that I should show the code screen again. I really need those. I've really enjoyed this. I'm really enjoying doing these streams and interacting with hardware. I think this is like my dream format for the videos that it could be. It's like working at a super low level, talking to hardware, doing it in TypeScript. So we fulfilled the name of the channel to some half degree, and yeah, so I'm really glad that you all also enjoy this. Come join me next week. It will probably be on Friday instead of on Saturday, but you never know. I might do it on Saturday as well. I'll try to make this a little bit more predictable in that I'll try to put the live stream up one day in advance, but we'll see. I'm not super good at these things. Thank you for watching, and I will see you next week.